But this is actually two people split one of these sheets because there are two copies on one sheet. These are simply extra graphing exercises. They are completely optional. You want, you do them. If you don't do them. So it's just okay. Alright. Today we will start with inverse trigonometric functions, which I promised because they were not in your basic function list. And to do those, of course, we need to look at the trigonometric graphs as they are, and then we'll see what we can do with those. Okay, so we'll start with the function y equals sine of x. Normally when we graph this function on a scale graph paper, we choose the scale, well, okay, we pretend, more or less, we pretend that pi equals 3, or rather that one unit on the y-axis is the same length as pi over 3 on the x-axis. In other words, the scale is slightly different on the two axes, which might create some confusion, a little bit of confusion, but not necessarily so. So it will be enough for our illustrative purposes. For illustration, it will be good enough. And so, this is pi, so this is half pi. So what you can do is you take your squared paper, if you have squared paper, and use two squares for 1 unit on the y-axis, so 2 squares equal 1 unit on the y-axis in the vertical direction, and 6 units correspond to pi on the x-axis. In other words, 3 squares is pi half. So if we want to measure accurately, then it turns out, so this will be 2 pi, this will be 3 pi halves, more or less like this. 1, 2, 3, that would be minus pi half, 1, 2, 3, it's minus pi, 1, 2, 3, minus 3 halves, 1, 2, 3, minus 2 pi. So this is how we prepare the system of coordinates for sketching the graph of the trigonometric functions, whether it's a sine function or cosine function or anything else. So we will need to sketch the trig functions anyway, so we could just as well do it now, and then it might be easier later. So now let's remember the graph of the sine function. We'll start with the graph of the sine function. If x is 0, sine of 0 is 0, so it's the point at the origin. Now, if x equals pi half, 90 degrees, pi half radians, then the sine value is 1. So it's this point. And then, when the angle is pi again, 180 degrees, then the sine value is 0. And when the angle is 3 pi over 2, that would be 270 degrees, then the sine value is minus 1 again. And when the angle is 2 pi, 1 full circle, then the sine value is 0 again. So we have some points, but if we just connect these dots, then we will get some zigzag kind of line. So some extra values of sine would be good. But, for example, we remember that if x is pi over 6, that's 30 degrees, or pi over 6 radians, it means that at that point sine value is 1/2. In other words, this is pi over 6, and this is 1/2 on the y-axis, so it will be this point. Practically the diagonal of the first square. Of course, in reality, it's not quite so because the scale on the axis It's not exactly the same, but for our purposes, it's good enough. For our purposes, it's good enough. So here we can also say that for 5 pi over 6 for 150 degrees, the sine value is again 1/2. And then when we go downwards, then of course it's again practically diagonal. So now we try to connect this all with a smooth line. This is one period of the sine function. And of course, we can imagine, copy-paste in our brain, we take this period of the sine function and copy-paste it on and on and on. Or as far as we have space on our paper. This, and with a little bit of practice, one learns to sketch the sine graph quite accurately. So this is the sine function. Now imagine if we had to find the inverse function of the sine. The graph should be actually symmetrical with respect to the line y equals x. Make it green, the line of symmetry. The graph of the sine inverse function should be symmetrical to this with respect to that green line. But that means that this function would have each point from the domain would have infinitely many y values, many y values for each x value. Imagine what would happen if we started doing the graph. Well, all right, I can sketch the graph here. -1, okay, something like this. But then, after this, I would need to go on with the graph and on and on and on with the graph like this. And we would be confused. This is not a function anymore. Because for each x value, we would have 1, 2, more y values. So that would not be a function anymore. So to make it 1-to-1, obviously we have to choose from this potential graph of the inverse function, we have to choose a fragment that would, let's say, cover all the possible values of the sine function. So it would cover the domain from -1 to 1. Remember, because the range of the sine function is from -1 to 1, the domain of the sine inverse function will be the same from -1 to 1. What is x for the sine function is y for the inverse function, which is called the arcsine function. And so we simply choose a fragment of the graph of this inverse function such that it covers all the domain of this inverse function and has one and only one value for each x. In other words, it is a function, no multiple values, no repetition. So this means we have to stop here, because after that we get repetitions of x values. So this part is the graph of the inverse function. The inverse function is called arcsine. So this is the inverse function of that, and it's called arcsine. What is arcsine of x?
At what point?
At what point we must stop? That's a very good question. So at the point where sine values begin repeating. At the point where the sine values begin repeating. For example, if we start from -5/2 to 5/2 for sine values, these sine values do not repeat themselves, and therefore we can safely reflect this part. We can safely reflect this part of the sine function to get the arcsine function, to get the inverse function. If I go on with the sine function, I see that the y values begin repeating themselves, which means I have to stop here. As soon as I see my y values of the given function, in this case of sine function, start repeating themselves, that's where I have to stop. To stop this from creating multiple y values. And so we can see that the arcsine function must have the domain of the sine function, of the arc sine. Domain of arc sine function is from -1 to 1, because those are the possible sine values that might happen at all. The only sine values that we can have are between -1 and 1, and therefore the domain of the arc sine function is just this. So only in this part, only in this, between these two values, -1 to 1, more or less. More or less with respect to the graph, because remember that this is not a very accurate graph, because I had to change the scale a little bit. So now if I want to reflect things, it's not exactly the bisector, it's not exactly this, but it's a bit deformed. It's not quite exactly that. So for the proper scale, if we have the same scale on both axes, for the same scale on both axes, you have the first sketch, the first graph. See, the graph of the sine function, this horizontal waves, and the graph of possibly arc sine function, vertical waves. And we see that this arc sine function starts being not a function. One x values, in this case, might have two different y values. It doesn't pass the vertical line test. The vertical line test. Remember, the vertical line must only intersect the graph of a function once, every vertical line. In this case, we would have infinitely many intersections, so that must be avoided. So the domain of the arc sine function is from -1 to 1, obviously. It couldn't be anything else, because this graph will never step outside that segment. It will never be outside this segment. But we have to limit the domain of the sine function for the sake of actually obtaining the function for the inverse. And for the inverse function, the range of the inverse function is obviously, well, because we had to cut it off here, the sine function had to be cut off here. This is where minus pi half to pi half. I had to cut off the sine function at x is pi half. This means this is where the arc sine function range is cut off. The domain for one function is the range for the other function. Now, because I had to cut off it here, that's where my arc sine range ends. So now, in this case, first of all the values of the sine function, all the domain is covered. And secondly, each of the values of x from the domain has only one possible value from the range. It's artificial. We had to do it artificially. We had to cut with scissors or somehow else. We had to cut off the rest of the sine graph, because otherwise we cannot have the inverse function. And that's how we obtain the graph of the arc sine function. Some examples for the arc sine function would be, for example, arc sine of 1/2. What do you think? What is the arc sine of 1/2?
Pi over 6.
Yes, it is the angle whose sine is 1/2, and the angle from this interval. So yes, pi over 6. Arc sine of 1/2 is pi over 6. I know that there are many angles more having the same sine value 1/2. So arc sine of 1/2 equals pi over 6 is equivalent. It means the same as sine of pi over 6 equals 1/2. That's why it's the inverse function. That's why it is the inverse function. And so arc sine can be taken off some numerical value, and the result, the function value of the arc sine is actually the angle whose sine we took for x. In a similar way, In a similar way, we can sketch the graph of the cosine function. For the cosine function, I will not do this vertical wave too long. I will simply figure out where we should cut off the graph of the cosine and just produce the graph of the arc cosine. So if this is 1 minus 1, 1, 2, 3, pi half, 1, 2, 3, pi, 1, 2, 3, 3 halves of pi, 1, 2, 3, 2 pi, 1, 2, 3 minus pi half, 1, 2, 3 minus pi, 1, 2, 3 minus 3 halves, 1, 2, 3 minus 2 pi, and so on. Okay, so the cosine values, we have to remember cosine of 0 equals 1. Cosine of 0 equals 1, it's this point. So remember that in the trigonometric circle, as we start circling, cosine of 0 equals 1. We look at the horizontal axis. Cosine of pi over half, pi over 2 of 90 degrees equals 0 because we project it to the x-axis. So this will be 0. At pi, it will be minus 1. So at pi, the cosine value will be minus 1. At 3 pi over 2, this angle is 0 again. And at 2 pi, full circle, it's 1 again. Alright, so the period, the shape of the cosine function is the same as the sine function. Of course, we can remember the values, but this was actually school stuff, so I'll try not to waste too much time on that. And here we have 0, here we have minus 1, here we have 0, here we have 1, and then we will have minus 1. Approximately. It's easier to graph on a sheet of paper with squares. So now, I have to make sure that all the values of cosine are covered and once, just once. All the values of cosine. So obviously I cannot take this fragment of the domain because here not all the values are covered and some of them are, well, almost all are covered twice. So what we do is, well, what would be the most natural domain for the arc sine, for the arc cosine function? From 0 to pi. See, if we take this part of the cosine graph, it again covers all the cosine values from minus 1 to 1. They never repeat. Outside this segment, they immediately begin repeating. So this is where we, well, I meant it as a symbol of scissors, cutting off. So we cut off, okay, with scissors. Cut off the graph here, cut off the graph there, and this is where we actually might start producing our arc cosine function. So obviously, because for the cosine function, the range for the cosine function is from minus 1 to 1, the domain for the arc cosine function, so the domain for arc cosine function obviously is the same as the range of the cosine function, again from minus 1 to 1, from minus 1 to 1, and the range of arc cosine corresponds to the limited domain of the cosine. The limited domain is from 0 to pi. Now the graph. We have to make sure it's symmetrical, all right. The axis of symmetry, and now let's see what we can get. So 0, 1 for the cosine means 1, 0 for the arc cosine for the inverse function, somewhere there. Pi half 0 means it's for the cosine function. It means that we need the point 0 pi half for the arc cosine function, this point. And so we would have this and this. See the symmetry, the green part of the graph and the symmetrical graph of the cosine inverse function. Technically speaking, of course, the arc sine, arc cosine might have infinitely many values. But because we want to talk about functions, we only take the principal arc sine and the principal of the main arc cosine, which means we restrict the domain and the range, the domain of the cosine function, which means the range of the arc cosine function is like this. So now we can see that the arc cosine values are only positive numbers from 0 to pi. And they cover the full range. They cover the full range of the values possible. If you look here in the paper, you have the graph of arc sine function only. And in the third picture, you have the graph of arc cosine function only. You see the x-axis is moved down so that the picture, the diagram can accommodate the full graph. So this part, that's the arc cosine function, the inverse of cosine function. And we might talk about, for example, arc cosine of square root of 2 over 2, that would be pi over 4, the 45-degree angle, whose cosine equals square root of 2 over 2, or if we want a negative value for the cosine, we could write arc cosine of, let's say, minus 1/2, arc cosine of minus 1/2, we can see it's more than pi half. So what is the angle whose cosine is negative half, minus 1/2? 120? Yes, 120. So it's 2 pi over 3. 2 pi over 3. So what we have to think is to think backwards. We have the cosine, now we are trying to figure out the angle. That's what the arc cosine function does. If we need to express more angles, we can always write arc cosine of this plus pi, or arc cosine of this plus 2 pi, or minus arc cosine of this, if we need other angles that are not within this range. The same goes for the sine function. The arc sine function produces values between minus pi half and pi half. If you need other values, you might write arc sine of this plus pi, arc sine of this minus 2 pi, and so on. In a similar way, we can define the arctangent and arc cotangent functions. Again, we should choose a good period or a good fragment of the original domain so that we can have a function 1-to-1. Now, can I erase this? I hope so. Now the tangent function. The tangent function, remember, the tangent function is not defined if you have to divide by 0. Remember that the tangent of any angle is the sine divided by the cosine of that angle. So at the x values where cosine equals 0, the tangent function cannot be defined. It's infinity. Right? If you have to divide by 0, you cannot divide by 0, so this is the problem that we have. So the tangent function is not defined for those values where the cosine is 0, which means it's not defined for plus or minus pi half, 3 pi halves, 5 pi halves, and so on and so on. Which means if I have, all right, 1, minus 1. This is pi half, and this is 1, 2, 3. Minus pi half. Remember that at pi half, the tangent function is not defined. We have vertical asymptotes, vertical lines towards which the graph actually strives, which the graph approaches, but it never intersects these vertical lines. Asymptotes, so the lines that cannot be reached. Okay, so the graph of the tangent, first of all, the period of tangent is just pi, unlike sine and cosine where the period is 2 pi. The period of tangent is simply pi, from minus pi half to pi half, and we might think that, for example, we know that if the angle is pi over 4, 45 degrees, then the tangent value is 1. So, alright, pi over 4, the tangent value is 1. If x is 0, then we have 0 divided by 1, it's 1. If we have minus 45 degrees, then we'll have minus 1. There are other values, but this is quite enough to for us to be able to approximately sketch the graph. So we can say that tangent is almost diagonal here, almost 45 degrees here at the origin. And the other parts, obviously for the tangent graph would go exactly like this. So we simply copy this period on and on and on and on. I will not do that. So for the tangent function, this is the tangent function. This is not the arc tangent function yet. So this is y equals tangent of x, consisting of many such branches. Now, how to construct the inverse function, the arc tangent function? Obviously, we need to choose again some segment which covers all the possible tangent values without repetition. Naturally, that would be this period, because all the possible tangent values from minus infinity to plus infinity are covered and they do not repeat, which would happen if we moved past the value pi half to one or the other side. So this means that the arc tangent, so now if I have the function arc tangent of x, it would have the range, the arc tangent, not the tangent, arc tangent. Arc tangent function would have, well, I should start with the domain, sorry, I started with the range. It will have the domain from minus pi half to pi half, but in this case it's an open segment. Previously, for the sine function, the segment was closed because minus pi half and pi half themselves were angles for which we can find sine values or the two perfectly good values of arc sine. In this case, the segment is open because at these 2 points, at the endpoints, minus pi half and pi half, the tangent is not. Sorry, this is the range. Oh. I'm confusing myself today. So the range of the arc tangent is our limited domain of the tangent function. And the domain of the arc tangent is what? The range of the tangent function is the domain of the arc tangent function. All right. For the tangent function, the range of the tangent function is what? All real numbers are possible. So the set of real numbers, which means the domain for the arc tangent is just that. The set of all the real numbers from minus infinity to plus infinity. The domain for the tangent, you know, what the natural domain for the tangent is different, all real numbers except for these pi half times an odd number. But because of this, we can write the domain of the arctangent. Because of this. What remains is to sketch the graph. So because the vertical asymptotes for the graph of the tangent were at minus pi half and pi half, for the graph of the arctangent, they will be the horizontal asymptotes. Remember, x and y simply switch places. So pi half, all right, horizontal asymptote not to be intersected, minus pi half, horizontal asymptote not to be intersected. And the graph itself, obviously symmetrical to this, so it means that we have to do something like this. So this is the graph of the arctangent, y equals arctangent of x. Now we can see that the domain is all real numbers. We can find the arctangent for any number at all, because anything can be a tangent value. But the domain, the range, the possible values of the arctangent are between minus pi half and pi half. And now you can guess very well what happens to the cotangent and arccotangent. Exactly the same thing. Exactly the same thing. Now the problem is that it would be extremely inconvenient to sketch 8 graphs in the same coordinates. Actually, I would be happy if I could use the same system for arccotangent and cotangent function, but that would make huge mess. All right. Remember that cotangent of x is actually cosine of x divided by sine of x, which means that the cotangent is not defined at the points where sine is 0. It means at the points 0, pi, 2 pi, 3 pi, minus 10 pi, whole number of pi's. Oh, very nice. Number of pi's. Okay. This is pi half, 1, 2, 3, this is pi. 1, 2, 3, this is 3 halves. 1, 2, 3, this is 2 pi. This would be 1, this would be 2, this would be minus 1. 1, 2, 3, 1, 2, 3, minus 5. 1, 2, 3, 1, 2, 3, minus 2 pi. Like this. So the asymptotes for the cotangent are at the points where we cannot have the cotangent values, where division by 0, which is impossible. So sine value is 0. If x is 0, 1 vertical asymptote. If x equals pi, sine of pi of 180 degrees. If sine is 2 pi, if sine is minus pi. So these are the vertical asymptotes for the cotangent function. Now, obviously, cotangent will be equal to 0 at the points where cosine is 0. Cosine is 0 at the points pi half, 3 pi half, minus pi half, and so on and so on. Now, about the other values of the cotangent. What about the other values of the cotangent? Cotangent of 45 degrees of pi over 4 is 1. So pi over 4, 1. This. And if we have 3 pi over 4, then that would be minus 1. So this means that the shape of the cotangent function looks something like this. I'm not going into too much detail simply because cotangent is more or less familiar from school and because of the previous paper on basic functions you had the examples of cosine graphs. By the way, I did email you the corrected paper. Then we might copy paste, and then we might copy paste, and then we might copy paste. So the graph of cotangent, we can see that the tangent function is increasing inside each segment of continuous function. Inside each segment of continuity, the tangent function is increasing. The cotangent function has exactly the same shape, but it's flipped, it's decreasing. And of course, these segments are translated, they are shifted. So this is the graph of cotangent x. So many of you know the cotangent function by its notation CTG. CTG. But I will be using the international notation, mostly cotangent. Something wrong? And now, of course, we have to choose, obviously, this part, because this would be a good thing to invert. So we can see that because if we take away all the unnecessary parts of the graph, all the unnecessary branches of the graph, leave only this one, the domain, the restricted domain, the artificial domain of the cotangent would be from 0 to pi, excluding the endpoints, because at 0 and at pi we cannot find the cotangent. So that will be obviously that will be the range of the arc cotangent function. And of course the range of the cotangent function, even within this segment, is from -infinity to +infinity. That will be the domain of the arc cotangent function. So now, obviously, if y-axis, oh sorry, I keep forgetting these. That's a crime. So, if y-axis is the vertical asymptote for the graph of the cotangent, then x-axis will be the horizontal asymptote for the arc cotangent. So, horizontal asymptote, the line not to be intersected, the line towards which the graph actually slides or tries to approach. And pi, well, somewhere approximately here. And now, without actually trying to do the symmetry or the flip, or we can try to do the symmetry, we would say that at pi half, this is the intersection point at pi half, and the graph should look like, okay. This is the graph of the arc cotangent. Again, on your papers, you have both the graphs of arc tangent and arc cotangent. No tangent cotangent graphs because they are on the previous paper with the basic elementary functions. I promised you to consider these arc sine, arc tangent, arc cosine, arc cotangent functions, because they are not always considered at school. So the function arc cotangent, y equals arc cotangent of x. So the domain of this function would be from -infinity to +infinity, all the real numbers. And the range of the arc cotangent function will be from 0 to pi, just like for the cosine, for the cosine function, except for the ends of the interval, the ends of the segments being open, not counted. Just like this. So that you know what these functions actually are and what they mean. Because when we do calculus, we will find the derivatives, we will integrate, we will differentiate, we will find limits and all kinds of things. But if you have no idea what this function actually is and what it means, then it makes absolutely no sense. Why should we differentiate the arcsine function if nobody knows what it actually is? Well, it's not so bad, as you can see, not very bad. At least if we understand that it's the inverse function. So if sine is the sine value for the angle, then arcsine is the angle value for the given sine. Similarly, arctangent is the angle value for the given tangent value. The opposite of what the tangent is. And the arccotangent is the angle for which this is the cotangent value. Alright, so this was about graphing inverse trigonometric functions. A little bit later, perhaps not today, let me check the time. Ooh, time flies. Which means that obviously we will not reach exercise 3. Notice there are two more trigonometric functions, the secant and the cosecant. The secant function and the cosecant function. They, well, in some systems, in some schools, they are simply not considered, simply because they are not really necessary. We have sine function, the cosine function, and the secant and cosecant are not so necessary, because we can do without them. On the other hand, it's useful to know what their graphs look like, and it's useful to know how they can be used in calculus. So at some point, well, obviously tomorrow, we will graph the secant function and the cosecant function and see how those graphs can be obtained from the sine and the cosine graphs. So some more transformations. Those transformations, by the way, are not mentioned here. So now, the basic graphing transformations. Vertical translation and horizontal translation. We did this more or less with the quadratic function already. So if you have a number b, add it to some given function, to a function whose graph you know. So we are supposing that we know what the graph of the function f of x looks like. We know perfectly what the graph is. And now, if I have a function f of x plus some number, what does it mean? It means that every y value gets increased by this number b. So this means the graph simply is shifted vertically, upwards, up if b is positive, down if b is negative. The same works for the horizontal shift. In this case, though, we have the function of x minus some value a. X minus some value a, which means that if you see, for example, y is the sine of x minus pi over 6. This would mean that you take the sine function and move it pi over 6 right to the positive direction, because the basic rule is f of x minus a means horizontal shift by a units, minus a. So notice the opposite signs. If you see x plus some number, it means the a value is negative and you have to move it left. This is again something that should have been covered at school. That's why I only gave you a table and overview of this. So if inside the function x has some number subtracted, then this number actually indicates the horizontal shift. And you have to pay attention to the opposite signs. In the vertical direction, the signs are what they see. In the horizontal direction, the signs are opposite. Now, what happens if you change the sign of the function? Simply write the minus sign in front of the function. The graph flips over, the positive parts became negative, the positive values of the function become their opposite negative values, the negative values become their opposite positive values. In other words, it's a reflection in the x-axis, a vertical reflection. You simply turn the graph upside down using the x-axis as the mirror. Using the x-axis as the mirror. And similarly, if you have function of minus x, it means that you do the same only horizontally. Only horizontally. The mirror is the y-axis. You reflect in the y-axis. So you can see that for the even function, this will not make any change at all, because for the even function, the graph is already symmetrical horizontally, so you can flip it over, it will be the same. For the odd function, you can see that if you change this, the sign of the function will change because the graph is not symmetrical against the y-axis anymore. Now, if you multiply the function by some number, supposing it's a positive number, let's assume it's positive, it means it's a vertical stretch, k times, stretch vertically. For example, if I have 3 sine something, it means I simply stretch it vertically 3 times. The x-intercepts, the intersection points with the x-axis remain the same, so the x-axis and the points on the x-axis remain in place, and everything else gets stretched 3 times. Of course, if k is less than 1, then the stretch becomes shrink. So we call it the scale factor. Scale factor greater than 1 means stretch. Scale factor less than 1, but still positive, means shrink. 1/2 of the function means you make it 2 times flatter. The graph gets flattened towards the x-axis. If on the other side, the number, the constant, is multiplied by x, not by the function itself, but only by the x inside the function. For example, if I have sine of 2x, this means horizontal stretch, but not 2 times longer, but 2 times tighter. So actually, the stretch by scale factor 1/m. So if we have f of m times x, then we can obtain this graph from the function f by applying 1/m as a scale factor. So if I have 2x, the graph actually becomes 1/2. So it actually becomes tighter. We squeeze, we shrink it horizontally. If I have f of 1/2 x, it means this graph is stretched 2 times horizontally, not shrunk. So this is again, we might notice that vertically the geometrical operation is what we might think. We add a number, we shift by that direction, by that distance. We multiply a function by a number, we stretch it that many times. In the x direction, if we add something to x, then we have to move it in the opposite direction. If we multiply something by x, we have to do the opposite. We do not stretch xy's m times, but we stretch xy's 1/m times. So it's the opposite to what might be expected intuitively. The first intuition tells us otherwise. In the x direction, you'll need to be very, very careful. Absolute values, finally, modulus. If I have the modulus of some function, then what happens to the graph? Let's think a little bit. It gets folded up. We fold the function upwards. Let's see. Suppose we have a function having this graph, for example. The given function is this, f. And now we want to sketch the graph of absolute value of f, modulus of f, modulus of f. So for the parts where the function f is positive, no changes are required. If the function is positive, then the modulus is still the same. So for the positive parts, the modulus is the same, and this part is also positive. So this part doesn't need to change. For the negative parts, where y values are negative, they must become positive and opposite. Positive and opposite. So we fold it up. So we simply fold this part up. And this part, yes, we fold this part up. So this red part is the graph of the modulus of the f function. And the black, so alright, I'll try to keep both black and red visible. Okay, it's not very accurate, but at least you get the idea. So the parts above the water level are fine. The parts below the water level must be reflected upwards because we can only look at the positive values of the function. And if we have, yes?
The question maybe just to make them positive, right?
Yes.
The modulus, yeah.
Modulus, the absolute value, of course. And finally, if we have the absolute value of x inserted in the function, the absolute value of x in the function, we will have, let's suppose we have some function. So now, if x is positive, then nothing changes. For positive values of x, this gives no change. It's the same function. If x is positive, we still have the same f of x. So for positive values of x, we simply copy the same function. Okay. So what happens if x is negative? What happens if x is negative? Yes, we fold over the y-axis. We don't need this because we can imagine. So for example, if x is this negative number, the function must have the same value as the corresponding positive x value. So at this point, the function must have the same value as here. So what happens is we discard the left side of the graph completely. We ignore this. It's not important. It's not important. Because for all the negative x values, the function will be the same as for the positive x values. And so we, okay, something like this. We discard this, ignore this negative part to the left of the y-axis, because alright, if the black one is f of x and the green one is f of absolute value of x. For positive x values, it's the same. For negative x values, it means that we have to put minus x in here for the negative x values, which means we need to reflect the positive x values here. The positive, the right-hand side part of the graph is folded over. And this is ignored, this is discarded, which sometimes is difficult to believe because people are well, rather stingy. We are sorry to discard anything. We always want to keep it. No, this is the one situation where we do not keep this part of the graph. So this gets discarded. Well, you don't have to cross it out. This is just my imagination. Let's say. Wait, now let's try. You can sketch in the same coordinates. So you have the graph of a function which consists of 1, 2, 3 segments, A, B, C, D. In the same diagram, in the same coordinates. Now, I gave you this line consisting of straight segments because it's very easy to transform them. So minus 2 f of x. So first of all, if the function value is 0, those points remain where they are. At point B, the coordinates are, I think, -2 and 1.5. So we take the point B and do what? First of all, reflect it down, because it's -2 times f of x, and put it 2 times farther away from the x-axis. So if it's 1.5, then the new function value at that point will be -3. So you can look at those numbers, you can look at those function values and simply change those points. People are restless today. Is it November? Is it something? Is it... No, the time change happened last week. Couldn't be. Couldn't be the time change. So the general idea is, okay, I have this, I have this, we have this, and we have this. So, something like this is what you have. This is the point A, B, C, D. You can also see the coordinates of those points. Notice, please, that 2 squares equal 1 unit. 1 unit is 2 squares, if you want to compare numbers. And so, the point in A, -2 f of x, because it's negative, we have to reflect, put it down, and because it's 2 times f of x, it must be, okay, 1, 2, there. Right, we reflect the point B, this would be B1, and A1 is the same as A. Now C is, I think, 1 unit below the x-axis, 2 squares. We have to reflect it because it's -2 times the function, and put it 2 times higher up. It's even above the B point. So we have now A remains there. This is C. You have done things correctly if you see that the graph intersects the x-axis exactly where the first graph does. And D, again, reflect it down and stretch it 2 times slower. So if this distance is 1 square, then it has to be below the x-axis and 2 times lower. So this is D1. We would have something like this. So the first graph would be something like this. You can do it in 2 steps if you like, if you have enough time and space. So you can, for example, reflect first and then stretch 2 times, or you can stretch 2 times first and then reflect. Or, because this function is so simple, you can do it all at once. B, f of x plus 1.5. What should we do to the, not to the red graph, but to the original graph? X plus 1.5 inside the function.
Move it by the x-axis.
Yes, move it left. Left, 3 squares, 1.5. 1.5 is 3 squares left. So that would be easy. 3 squares left. Okay, 3 squares left, 3 squares left. 3 squares left. 3 squares left. Okay. That's easy. That's easy. Simply move it 3 squares. And, oh yes, we would need to. Okay, this was -2 f of x, and this one was f of x plus 1.5. Notice that we actually moved it left. So the shift is by -1.5. The shift is by -1.5 in the negative direction. Absolute value, modulus of f of x. So we leave the upper part of the original graph where it is, and what's below the x-axis, only this small triangle, only this small triangle gets reflected upwards. So that would be C, absolute value of f of x. So this part is good, this part is good, this part should be reflected upwards, and this part is good. So now this graph is absolute value of f of x. And finally, function of modulus of x. What does it look like? What does it look like? Remember where we have modulus of x? What did we do? Leave the right part of the graph to the right of the y-axis, discard the left-hand part and reflect the right-hand part. Which means all I have to do is, I'm not going to sketch it because I have no more colors for the sketch. I have no more colors for the sketch. I simply take this part, starting from the y-axis, and reflect it there. The black part is discarded. This part is discarded, so I have this, and the graph will simply look like a very flat V. Like a very flat V. Up to the y-axis. The vertex of the V will be on the y-axis. Not at C, but here. This is the breaking point. This is where we break it up. So we ignore the left part and we only take this segment and reflect it to finish the graph. So this exercise was, of course, well, more or less abstract. The function was simply given in a sketch so that you could perform some of these operations and understand what's going on. Now in exercise 2, we have 15, 17, how many minutes? I have the answers for exercise 1 and for exercise 2. So I will email those probably this evening. I made them, well, I did make them on the computer. I didn't sketch by hand. But what you need is to make sure that you have graphed them correctly. So that's the okay. So the basic function is x squared. You might or might not graph it, but remember, for the quadratic function, all we need is to find the vertex. So x squared plus 3, we did something like x squared plus 3, or maybe we did not. Maybe it was plus 4 or 4 minus x squared or something. So these functions, actually, these quadratic functions simply, let's say, hopefully, somehow, fix things in your minds, more or less. So x squared plus 3 would be a parabola shifted 3 units up. X plus 2 squared would be a parabola shifted 2 units left. The third one, x minus 2 squared minus 3, will be 2 shifts, so 2 units right and 3 units down. And again, for a parabola, remember, it's very easy because all we need is to know the vertex and the direction of the ends up or ends down. And you can count the squares. Remember, you can count the squares for a parabola, 1, 3, 5, 7.
So how can we go?
Yes, I know there are applications. Of course, you can check it. No, it's okay. You can check.
What check? No, I mean the H one.
H. Oh.
Yeah. Just.
Oh, H. H is very nice.
Really, it's very nice. I see.
So, all right, we have, let me see, 15 minutes. You want to start with H?
Yeah.
Yeah.
Okay,
Right.
2 people do. The rest don't want to do anything at all, I say. I can see. But the thing is that you will need to be able to do this. Actually, G and H, they would need to come in that order, but okay, let's do H. Let's do H. And then those who feel happy enough. Now, there are a lot of graphs. There are a lot of graphs, and you should do them for practice. Remember that on Thursday I am bringing you homework, graphing and functions. So, my favorite, H. Y equals 2x plus 2 over x plus 3. Now, I'm going to be extremely clever and cunning. I'm going to transform this function into something recognizable.
Into a hyperbola.
Yeah.
2 times x plus 1.
Exactly. Well, not exactly. I will do 2 times x plus 3. Yes, of course it's wrong. So I have to subtract 4 to get the right answer, right?
Okay. Now I get the idea.
Okay, so now we see, if I divide this part, it's just 2. If I look at this part, it's minus 4 over x plus 3. Or I can write it's minus 4 over x plus 3 plus 2. Which means I can start with the graph minus x plus 4, minus 4 over x. The given function will be this. This is, or I will write f of x. Actually, I'm rather a poor filming material because I keep correcting myself and making mistakes and improvising and
As
doing.
long as it's on camera.
As long as this is what you can see. All right. Okay. So we start with this, but this will actually be f of x plus 3 plus 2. So what we need is a hyperbola and a horizontal shift and a vertical shift. So this type of function, linear quotients or quotients of linear functions, actually the graphs are always hyperbolas because we can always perform something like this. Well, how clever you have to be to find the correct numbers, that's a different question. But generally, we take this before brackets. In the brackets, we always put the denominator, close the brackets, correct your error. And so, there will be a second trick. So minus 2 and 2, this point, 4, 1, 4, minus 4, 1, like this. So this is the parabola, hyperbola, 1, 1, 2, 1, 2, this, 1, 2, 1, 2, 1, hyperbola, all right. And now, this time, I did not forget to mark the axes x and y. This time, now, kindly imagine yourselves in a train. So the train is just going somewhere, going. If the gate of the train, if it's smooth, you might imagine that the train is standing still and the trees are running backwards outside the windows. So this is what we are going to do. This is the train which should go minus 3 plus 2, minus 3 plus 2. But we'll say, okay, let's make the train stand still and the trees go backwards. In other words, let's move the system of coordinates. This should be moved by minus 3, 2, actually by the vector minus 3, 2. The translation, the shift is actually in translation by some vector, minus 3, 2. But in reality, well, how do you know that the trees are not the ones running backwards? Perhaps the train actually does stand still. I will move the trees 3 minus 1, the system of coordinates, in the opposite direction by the opposite vector. So instead of moving the graph horizontally 3 units, I will move the system horizontally right 3 units. The graph would have moved left. I move the system 3 units right. So this will be the real x-axis. This will be the real x-axis. This was simply a preliminary x-axis, not the real one, x prime. If you have marked, you can rename it x prime. It was simply a preliminary x-axis. This is the preliminary y-axis, y prime. And the y-axis, the graph should move 2 units up. So it means I move the system 2 units down. This will be the real x-axis. And now,
So x prime must be on the right.
yes.
But you,
No, you see
you have
the
written
function.
y
Oh yes, it has to be the other way around. Right. Sorry. The function had to be moved right, and the x-axis had to be moved. The system had to be moved. This is much more. The system had to be moved in that direction. Yes. So the graph moves 3 units. There, I was right.
No, you're gonna move.
Yes.
2 points up.
I have to
and
move the
left.
graph 3 units left, which means the system must move 3 units right. I was correct.
No, I mean, why did you write the y prime at the horizontal axis?
Ah, sorry. It was the other way around. Yes. Okay. Okay. Because I was trying to keep too many things in my mind at the same time. Okay. So now, what we can see, of course, now we can put the actual numbers on the actual axis. So this would be 2, and this would be -3. So we can see that those preliminary axes, x prime and y prime, now have become the asymptotes. Well, if you move a graph, then you should move it along with its asymptotes, so that the graph has some framework. It's like the asymptotes are more or less like handrails when you are walking in the staircase up or down. So you have this handrail. So you can imagine that the asymptotes are the handrails for a graph, so that it keeps some kind of frame in the correct perspective. So of course, you may graph the function -4 over x, and then think, okay, I have to move it like this. You should sketch the asymptotes through this point. Sketch the asymptotes through this point, and then move the graph point by point. Re-sketch the graph after the shift, after the translation, which is of course quite messy. Basically, if you are only dealing with shifts, you can apply this method of moving the trees instead of the train to any function at all, or if you only have one function and several transformations, if you can afford to leave the translation, the shifting, to the last, then it's okay. In the end, you move the system. If you have more than one function and they all have different shifts, then this will not work, because in the end, as soon as you adjust the system for one function, the other functions don't work anymore.
Sorry. You told us before that if we multiply something to x, then we have to move left. But here you moved right. If we add something to x.
Yes, we have to move the graph to the left.
Yes.
And if this is my original system, then the graph has moved left, because the system gets moved to the opposite. So the train is going to the left, but the trees are running backwards to the right. So the whole thing, this trick of instead of moving the graph in the correct direction, we move the system in the opposite direction. That's why. The graph has moved. The graph has moved. The thing is that it was here, it has moved. I don't see it in the old place anymore.
There.
But that shouldn't be a problem.
So
That shouldn't be a problem.
yeah, move to the right. So move to the positive.
So the trick is, imagine you are a small child sitting in a train and watching the trees running backwards. The train is the graph, and the trees represent the system, and that's what you do. So that's a very useful trick. It's not strictly necessary. You don't have to do it like this if you don't like it, but it's useful. It's useful. Or you can start by sketching the asymptotes through this point and then imagine that that is the system of coordinates for -4/x and sketch the graph in that new system of coordinates, which means in the old system it will have moved. There are variations to this method. And the thing is, the one thing that does not work, is making a table of values and plotting it point by point. Because in that case, you will inevitably make a mistake and connect the wrong points in the wrong order. I've seen it happen again and again. So before you start graphing any function, there's one single thing that has to be very clear. What kind of graph it will be? What kind of function? What will it look? What in general will it look like? Otherwise, you might be stuck. You might start connecting the wrong points. You know, like those children's books where you have to connect the dots in the correct order to create a picture. If you do it wrong, you get the wrong picture. So that's the important part. If you look at the function, if you understand basically what it should look like, then the rest is just follow the table, just follow these things. So yes, I will email you the answers for exercise 1 and 2, and try to do independently as many as you can before you start comparing. Before you start comparing the pictures I send you. And tomorrow we will do 3, 4, 5. 3, 4, 5. And if you like some of those extra exercises, you can take those too. That should be enough, I hope. Yes.
Can you email the answers for this optional
For later. Today you will get all this exercise for number 2 and 1.